All right, students. So the next type of titration that I wanted to talk with you all about is the titration involving a weak acid with a strong base. So for such titrations, the weak component is always the analyte. Okay, so that's the one that goes in the flask, the weak component. Whether you have a weak acid or a weak base, we'll see that both of the weak, like either of the weak components always go into the flask. Okay, and that said, then the strong component is always the titrant. It goes in the burette. Okay, so strong goes in burette, weak goes in the analyte. Okay, it goes in the flask. All right. Now, if we plot this weak acid strong base titration, what we'll do is we will start acidic and then we will gradually become basic as we add more and more volume of our strong base. And that just sort of makes sense, right? In our flask, we start out with a weak acid, of course it's acidic, and then gradually as we add more and more of that titrant, of that strong base, it will become more and more basic. Okay, now for this type of titration, okay, the steps to solve these types of problems are to write the known concentration and volume, so just like what we did before with our strong acid, strong base. Okay, the next step is where things become different. Okay, we will be identifying the titration type as we did before, but this time, since we find that it is a weak acid, strong base, it will be a two-part or a big two-part problem. Okay, so for the first part, we'll do a stoichiometry part using a before and after table. Okay, and then if it is weak, right, if it's still weak after that, right, then we'll establish equilibrium with either an ice table or the Henderson-Hasselbalch equation, depending on what information we have available. All right, and then for step 3, we set up those tables and solve, okay, for what we're looking for, whether that be our concentration of H or our concentration of OH or what have you. Okay, and then from that, you'll get your pH. All right. So let's work through an example. Right now, this example is going to be on slide 15. Okay. And for this, right, we will need to find our pH after we add 0.00 milliliters, 12.50 milliliters, 24.50 milliliters, 25 milliliters, and 40 milliliters. Okay, so these are going to be trials, just like what we did last time, right? But this would be trial 1, 2, 3, and so on. If we add these volumes of 0.400 molar sodium hydroxide to 50 milliliters of 0.2 molar HCOOH. All right, now I'm just going to call this HA, and that is a weak acid. Okay, since it's a weak acid, okay, we may also need our Ka for that, which happens to be 1.8 times 10 to the negative 4. All right, now, how did we say that we started this problem? Well, the first thing that we're going to do is, since we're dealing with a titration type problem, or we're adding various amounts, what we're going to do is first write our volumes and concentrations. Okay, so we have a volume of acid of 0.0500, 0.0500, okay, liters. We have a volume of sodium hydroxide equal to 0 liters for trial 1. All right. our concentration of acid at the beginning is equal to 0.20 molar, and our concentration of sodium hydroxide at the beginning is equal to 0.400 molar. All right? Now, in step 2, we need to determine the type of titration. Okay? Now, the type of titration in this case is a weak acid, strong base titration, right? So that means that we're going to follow the other procedure, which involves 2 steps, right? The first step involves a stoichiometry part, which means that we need a before and after table, okay? And step 2 is either going to be, since it's weak, right? It's either going to be an ice table or the Henderson-Hasselbalch equation, okay? Now, since we don't have any base that was added, right? So since we don't have any base, that means that we're going to be using the ice table, okay? Because we don't have all of the information here to get our Henderson-Hasselbalch equation, all right? And you'll see why in a second, okay? Now, let's do our before and after table, right? So part 3 is setting up our tables, right? So we do our ice table, then we have HA in equilibrium with H plus and A minus, all right, BCA. Now, since we're dealing with a before and after table, are these going to be concentrations or are they going to be numbers of moles? Here, we need moles, right? Moles for before and after, okay? Now, in this case, all right, we can take our, or rather, let me think about this. I'm sorry. Yeah, we don't need a before and after table, right? And why don't we need a before and after table? We do not need a before and after table because we haven't done anything to change our stoichiometry, right? So our before equals our after, okay? So in that case, whatever we started with is what we're going to end with because there's no change in our before and after, right? So that means this needs to be our ice table, okay? And in this case, our initial is going to be whatever we started with, right? Or whatever we ended with in our before and after table, but since we didn't add anything, it's not going to change it. All right, so in that case, for this type of table, right, for an ice table, these can be in concentrations, right? I'm just going to make this first part pretty easy. All right, so we have HA, which is 0.20, concentration of H plus, 0, concentration of A minus is 0, 1 times negative x, 1 times positive x, 1 times plus x, giving us x, 0.2 minus x. We have our Ka, right? Ka is equal to 1.8 times 10 to the negative 4th, which is approximately x squared over 0.2, where I've dropped the x to make our 5% approximation, right? So doing this, I see that my x is equal to 0.060, which is pretty cool, right? So if I take that to check my 5%, then I'm going to get 0.06 over 0.2 times 100, which is equal to about 3%, which is less than 5%. So we can use that x. Now that x happens to be equal to my concentration of H plus at equilibrium, which means that I can then solve for my pH, which is equal to the negative log of 0.0. Oh, I don't know. I did it right. Yeah, I did. 0.06 equals 2.22 as our pH. Okay? And that's low, it's acidic, that should make sense. All right, the next step will be when we add a little bit of our base. So in trial 2, okay, we've now added 12.50 milliliters. All right, so the volume of sodium hydroxide is equal to 0.0125 liters. We have a volume of HCl, which is equal to not HCl, the volume of HA equal to 0.0500 liters. And we have a concentration of sodium hydroxide equal to 0.40 molar. We have a concentration of HA equal to 0.20 molar. All right, again, both of those are our initial ones. Okay, so that's step 1, writing out our initial concentrations and volumes. All right, what's our next step? Next step is to identify the type. All right, and our type is weak acid, strong base. Okay, cool. So that means it's going to be 2 parts. Part 1 is going to involve a before and after table, right? And part 2 is going to either involve an ice table or the Henderson-Hasselbalch equation, depending on what we have. So step 3, right, is setting up those tables. So let's do our before and after table. We do have to do this time because we have added a little bit of base, which is going to change our stoichiometry, right? So this is our stoichiometry part, right? So let's set up our before and after table. In our before and after table, we have HA plus OH minus. So we've got both of those components that we've added, right? So then that gives us H2O plus A minus, okay? So now we have before, change, after. Okay, so here we won't need any of our water, right? And in this table, do we need moles? And the answer is yes. We'll need to convert to moles for this one. All right. This one looks like it's dying, so I'm going to switch out to black. Okay, so we need moles, right? And if you remember, when we get moles, we're going to take N is equal to M times V for each species. Okay, so in this case, we have NHA is equal to 0.20 molar, right? That's going to be our M for HA. And then we're going to have 0.050 liters, which was our volume for HA. So that will give us our number of moles as 0.010 moles of HA, which I can then put into my table, 0.010 moles. Okay, the next thing is going to be solved the same way, which is our sodium hydroxide, which is equal to 0.40 molar times 0.0125 liters, which gives us 0.0050 moles. In this case, it's OH minus, right, because that completely dissociates, and it's 1:1. That goes here, so we have 0.0050 moles. Notice how I'm putting moles instead of molarity, okay? And we started out with none of our conjugate base, okay? Then step B, right, is to subtract and add, depending on our limiting reagent. Limiting reagent. Okay, so which one is limiting? It's going to be the smaller of the two, which is the 0.0050 moles. minus 0.0050. And over here, it will also be added, plus 0.0050. So adding those all up gives us 0.0050. Here we end up with 0, and here we end up with 0.005. 0 moles. Now, that's in moles, okay? Now, if you recall, right, what is our Henderson-Hasselbalch equation, right? Well, Henderson-Hasselbalch is pH is equal to pKa plus the log of base over acid, right? Those were specifically our concentrations. So if we think about it in terms of our acid and conjugate base, we now have HA and we have our A minus. We couldn't use this equation for trial 1 because yes, we had the Ka and yes, we had our concentration of HA, but we did not have our concentration of A minus, okay? We didn't have any of that because we hadn't added any of our base and we hadn't established our equilibrium yet, okay? So in this case, now we have these two and we have our Ka. So now if we want to solve for our pH, right, we're going to do our Henderson-Hasselbalch. So we have pH is equal to the negative log of 1.8 times 10 to the negative fourth plus the log, and these need to be concentrations. So what we will have is we will have 0.005 moles all over our total volume, which our total volume in this case is those two numbers added together, which is 0.0625, okay, liters. All right, and then 0.005 moles over 0.0625 liters. Those happen to be the same, so you end up seeing that your pH is equal to 3.745. Okay, again, last time it was 2.22. All right, our pH has gone up a little bit because we've added some base. All right. Now, I'm going to skip trial 3 for the sake of time. But I will continue with trial 4. Hopefully we can get this done quickly. Looks like I erased a little bit of my stuff, but we had 0.4, and then we had the Ka was equal to negative 1.8 times 10 to the negative 4. Okay, so we're looking at trial 4 now. So the very first thing that we're going to do is write our concentrations. We have a V of sodium hydroxide equal to 25 milliliters. We have a V of HA equal to 50 milliliters. We have a concentration of HA at the beginning equal to 0.20 molar. We have a concentration of sodium hydroxide equal to 0.400 molar. All right, step 2, again, like before, strong base, weak acid, right? So you're going to have a choice of either ice, well, it's 2 parts, right? The first part is stoichiometry, and the second part is either ice or Henderson-Hasselbalch, depending on your conditions, right? And you continue to solve. So, again, we're going to need our number of moles, right? So we need moles because we are doing a before and after table, okay? So, since we need moles, N of sodium hydroxide and N of HA. I'm not going to show you how to do these again, but basically it's M times V, Okay, so if we're doing m times v, we get 0.010 moles. Here we get 0.010 moles. When we do our before and after table, what we see is we have HA plus LH, all right, which is in equilibrium with H2O, and A minus, all right, BCA. As you can see, a lot of them are just the same steps over and over, so you just got to know when to use them, right? And again, we're going to ignore water, so I'm going to move this over just a little bit for the A. Okay, we start out with none of that. We have 0.01 and 0.01. We're going to subtract 0.01 from both sides. And, well, not from both sides, but from the left side. And we will add 0.01 to this side. We will get 0.01. And here, we will end up with 0 and 0. So we don't have any HA or base, right? Well, what do we do now? At this point, we have to do an ice table, but this is what's going to interact, right? Because this is the conjugate base of a weak acid. If you remember back from our discussion of salts, if we have a conjugate acid if we have a conjugate base of a weak acid, it's going to pull out any of those protons that are in solution, right? So for part 2, we do an ice table, okay? Starting with A minus. Now, A minus plus H2O, what does that do? Well, that goes to HA plus OH minus, right? Remember, we're treating this like it goes to completion and then establishing our equilibrium, okay? So now we do ICE. To fill these, we have to have our concentrations, right? Whereas before, we were dealing with a number of moles. Okay, now here we're going to cut out our water, right? We don't need that. Now, this is our number of moles, right? So if we take our number of moles, 0.01 moles, and we put that over our total volume is going to be equal to 75 milliliters, 0.075 liters, okay? And then that will give us a concentration of our acid, which is 0.133 molar, 0.133. Now remember, we assumed that it went all the way to completion, so we have no HA and no OH minus, okay? At this point, we are going to do our standard steps where we say, okay, minus X plus X, 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 0.133 minus X. We have our Ka, okay? But is this the process for Ka? No, this is the process for Ka. This is the process for Kb. So now we need to have Kb in order to set up this equilibrium expression, right? Kb is equal to Kw over Ka, which in this case is equal to 5.56 times 10 to the negative 11. And that happens to be equal to x squared over 0.133 minus x, which we're going to, of course, approximate. And if you do all this stuff, you will end up seeing that x is equal to 2.72 times 10 to the negative 6. 2.72 times 10 to the negative 6. And that is our concentration of OH minus. Okay, so now that we have our concentration of OH minus, at equilibrium, that is 2.72 times 10 to the negative 6. We can get our POH, right? Because that's going to be the negative log of that number, 2.72 times 10 to the negative 6, which is equal to 5.565 Okay, and now our pH finally is equal to 14 minus pOH, which is equal to 8.434. Okay, again, we've started climbing beyond our acid region as we've added more and more base. Okay. So that happened when we had an equal number of moles of acid and base to start with. Okay, and it still made it a little bit more basic simply because of the fact that we had that conjugate base of a weak acid. It made it even more basic. Okay? Now, let's try to do trial 5. Okay? For trial 5, right, the first thing that we're going to do is, as always, concentration of base, 0.04, or sorry, it's the volume of base, 0.04 liters. We have a volume of acid, which is 0.05 liters. We have a concentration of base, which is equal to 0.40 molar initially. And we have a concentration of HA initially, which is equal to 0.20 molar. All right, and as before, you have a weak acid, strong base, which means you are going to do parts 1 and 2. Okay, again, this is going to be your stoichiometry part with a before and after table. And part 2 is going to be either an ice table or Henderson-Hasselbalch, and the whole point of that is to establish equilibrium. And you have to do that part simply because of the fact that we have a weak component in our system that's going to shift back to equilibrium once we've done our initial stoichiometry part. Okay, so very first thing is going to be to do our stoichiometry, right? And for that, we do a before and after table. This is part 3. For our before and after table, we have HA plus OH minus in equilibrium with H2O plus A minus. All right, before, change after. Ignore the water. All right, since we're doing before and after, we're going to need our number of moles, right? This number of moles is 0.01 moles, right? If you multiply those together, you get 0.016, okay? So the moles of hydroxide ion are equal to 0.016. So we're going to put those in, 0.016 moles. We've got 0.01 moles. And over here, right, we started out with nothing, yes? So that means that we cannot use our Henderson-Hasselbalch equation at the very beginning, right? So we'll have to wait until afterwards to see if we may be able to do it, okay? Because we didn't have this component, all right? Now, in our change, we're going to pick the smaller of the two components. Notice that this time it is our acid. So minus 0.01 minus 0.01 plus 0.01, because again, that's products. All right, so we have 0.01. Here we have 0.015. And here, and actually, sorry, that was wrong. We have 0.06, right? Because I can't add. All right, and now we have 0 here. Now, notice that we have a weak base, right? So we may have to do the equilibrium, but we also have a strong base, okay? If you have these two, all right, strong base always wins. Okay? So that means you can jump straight into calculating your POH, okay, using that, because regardless of what this is going to dominate, okay? So that means that this is going to be the negative log of our concentration of OH minus, which we have. So that's going to be the negative log of 0.06, sorry, 0.006, which in this case, oh, that's not right. And why isn't that right? Because these are moles. So we actually need to calculate our concentration of OH minus, which is equal to 0.006 moles. And again, that's why you should always write the units for these particular tables to keep yourself straight. So that's moles. And our total volume in this case is 0.090 liters, which gives us a concentration of, let's see, 0.0667 molarity. All right, that's 0.0667. That goes in here. Negative log of 0.0667, which is equal to 1.18. That's again our POH. So to get our pH, that's going to be equal to 14 minus our POH, which is equal to 12.82. Again, now we are very basic. Okay? Again, strong always wins when you've got that competition. So it can help save you some steps if you know what you're doing. All right? So with that, that concludes our discussion of the weak acid strong base titration, which will be on your quiz. Again, shoot me some emails if you have any questions, and I'll be happy to help you all out. All right? Good luck.